Hello everybody, welcome back to another video, and today we're going to be going over how to find the limit of a sequence. So this is the second part in the real analysis series, and we're going to learn how to do epsilon n definitions. So let's get started. So our first problem is we want to prove that the sequence a sub n equals 1 over n converges to 0. So as n reaches infinity, 1 over n, as the numbers go up, the 1 over n is going to get closer to 0. So the definition is pretty similar to epsilon delta definition, except we have n instead of delta. So it's going to look like this. For all epsilon greater than 0, there exists a big N in the set of natural numbers shown with the double bar n, such that n, this is going to be a little n, is greater than big N, which implies that the sequence minus, in this case, 0, because that's what we're trying to prove that it converges to, is less than epsilon. And it might not make sense right now, but after I explain what all these symbols mean, it'll make a little more sense to you. So for all epsilon greater than 0, there exists an n in the set of natural numbers. And the reason why it's in the set of natural numbers is because when we're talking about n and big N and little n, we're talking about the number of sequence. You can't have a 1.5th term in the sequence, so that's why they're in the set of natural numbers. And you can't have a 0th term and things like that. So we're saying that there exists an n in the set of natural numbers where n is less than a little n. So basically what it's saying is that there exists a term that comes after big N. So this means that, for example, if you're on term 4 trillion of the sequence, there exists a 4 trillion th term. And so what this says is that our sequence minus the convergence, or the distance from the sequence to its convergence point, right? Because we're trying to prove that 1 over n converges to 0. So the distance from 1 over n to 0 is always less than epsilon. Epsilon's a super tiny number, super close to 0. And ideally it would be 0, but obviously since it approaches, then that means that the sequence must be a number distance away from epsilon. So how do we go about solving this, proving it? So one way to do this is, let's first work with the expression that we have here. So our a of n minus 0 is less than epsilon. So what this is saying is that as 1 over n, or let's say we have our 1 over n, as it approaches 0 over here, it's going to be some distance epsilon away from 0, which is a super small number, away from 0. So all we need to do is look at the information that we have, plug in all our info, and then we need to set our variables correctly so that we can prove that there is a next term in the sequence for any term in the sequence. So we're going to have the absolute value of our sequence. Our sequence is just whatever sequence you're trying to prove. So in this case, 1 over n, and then minus 0 is, of course, just minus 0. And this absolute value of 1 minus n, just to simplify things, the absolute value of 1 minus n is always 1 minus n because the absolute values do split in the fractions. So that's what it looks like. So now, after you've simplified the expression, sometimes it could be a little more complicated if it doesn't converge to 0. But once you've simplified the expression, we want to choose an n. So we want to choose n. So when we choose n, we have to think. We want 1 over n, which is this part right here, to be less than epsilon. So we want 1 over n to be less than epsilon. Okay? And that implies we can also transform this expression to say we want n to be greater than 1 over epsilon as well. And this is simply by reciprocating both sides and accounting for that reciprocation by changing the sign. So we want n to be greater than 1 over epsilon. And so that means that, as from our assumption up here, we said that there exists an n in the set of natural numbers such that n is greater than big N. So we have what we want here. We're just missing the n. So we just got to make this n. And then we've proven our sequence. Now what we need to do is we want to say n is equal to the ceiling of 1 over epsilon. And the reason why it's the ceiling of 1 over epsilon is because when you have a ceiling function, it rounds up the number. So if epsilon is for example 3 or 0.3, right? 1 divided by 0.3 is 3.3 repeating. And so if we take the ceiling, we get 4, because we can't have a 3.3 term of a sequence. So this just ensures that it will round up to an integer that we can actually use. So we're going to let n equal the ceiling of 1 over epsilon. So if that means that also implies that n, which is 1 over epsilon, is less than little n. So that means that the sequence converges to 0. And we just proved it. All right, let's move on to another example. And if you're still confused, it will get better over time. You just have to go through a few examples. So the definition is very, very constant when it comes to a sequence. So for all epsilon greater than 0, actually, in fact, I'll write it up here. For all epsilon greater than 0, there must exist an n in the set of natural numbers such that n, little n, is greater than big N, which implies that the distance between the sequence and 0 is less than a small number, a super small number like epsilon. So now it's just going to be very important to just go through the motions again. So let's first fiddle with our b of n minus 0 component here. So b of n in this case is -1 to the n over n. So the absolute value of this, well, since this would be an alternating sequence where one term is negative and one term is positive, because we're always taking the absolute value of this sequence, it will always be positive. So that means that this is equal to 1 over n. In other words, because 1 raised to the n is always 1. Of course. So now, this is actually a similar situation to the last problem. We want to choose our n. We want to choose our n. So we want 1 over n to be less than epsilon. And we want, which means that we want if we reciprocate both sides, that means we want n to be greater than 1 over epsilon. So now the only logical move is to make big N 1 over epsilon, and now we say that n is greater than big N. And that also, combined with 1 over n being less than epsilon, proves that it converges to 0. So let's move on to our last example. This one will be a little bit different. So we have C of n of our sequence, which is n over n plus 1. This converges to 1. So we have, for all epsilon greater than 0, there exists a term in the sequence such that there is a greater term in the sequence. So in this case, this will be C, the distance between C of n and 1, and this is less than epsilon. I know I'm running out of room over here for it, but y'all get the idea by now. So let's first fiddle with the C of n minus 1 part. Is what we need to relate back to. So C of n is n over n plus 1. And then we're going to be subtracting 1 from it. And this is a little bit different because we can't just take the absolute value immediately and change the negative 1 to positive 1 or do anything like that. We have to combine our terms. So let's make a common denominator. So this is going to be n minus n plus 1 over n plus 1. Because now n plus 1 over n plus 1 is guaranteed to be equal to 1 in this case. So now we have this expression. We can now just simplify things down. N minus n is 0, and we just have a negative 1 up here, so negative 1 over n plus 1 in absolute value. And we can just split the absolute value, and we get 1 over n plus 1. So now we want to choose an n. So when we choose an n, we want to make 1 over n plus 1 less than epsilon. So if we invert it, if we invert both of these and change this the symbol, we have n plus 1 is greater than epsilon, or 1 over epsilon. We're getting close. We do have the n on the greater side. So now all we need to do is just move the 1 to the other side. So now we have n is greater than 1 over epsilon. minus 1. And so we're going to set n equal to the ceiling of 1 over epsilon minus 1. And now that we've done that, we can conclude that there does exist an n that is greater than n that satisfies that the distance between the sequence and 1 is actually smaller. Anyways, I'll see y'all later, and goodbye.